Alrighty, so we're going to continue with the discussion of physics with rotational motion. Last time we did rotational kinematics, which was kind of like the first topic of physics we did, kinematics, only when things move in a circle. Now what we're going to do is similar in discussing forces. So we did Newton's law before. But instead of normal forces, these forces are going to be those which cause things to rotate. So for instance, if you have a bolt and you put a wrench on the bolt, and generally speaking, you either want to tighten the bolt or you want to loosen it. And the way you do it is, of course, you apply a force. That makes the handle of the wrench rotate, and that, of course, applies some force to the bolt, which makes the bolt rotate. Well, that specific type of force, the force which makes something rotate, is called a torque. The Greek letter tau is the variable for it. An equation, I'm going to write in a very specific way, is R cross F. The units, Newton meter. So force times distance, newtons times meters, that's the units for torque. Now, let me just say, R stands for distance. F, of course, is force. Now, if you think about it, we've already had a thing in physics, which is defined an equation, which is force times distance. If you remember, we had work. Work, we had force times distance. And I said very specifically that this is a very special type of multiplication because we're talking about vectors. And with vectors, the math may be a little more complicated. And what I said is because force is a vector and distance is a vector, this was a vector multiplication called the dot product. And what it actually meant, deep down, was when you go to multiply the force and the distance, what you need to multiply is how much of the force is in the direction of the distance. So it's kind of like saying the amount of force parallel to the distance. Okay, if the object moves to the right, then you need to know how much of the force is either to the left or to the right. And if the force is at an angle, then you figure out the x component of the force. If the object moves down, then you need the y component of the force, and so on. Well, here we have something different. Now what we have, torque, is R cross F, where, of course, force is still a vector, and the distance, and we're calling it R for distance, that's just the standard notation, but it still means distance. The distance R is also a vector, so this is another type of multiplication, a second version of multiplication. It's completely different from the dot product, and it's hard to think about it when you're so used to normal math with numbers. You know, you multiply, there's only one way to multiply. 3 times 5 is 15. There's no different types of multiplying, it's just multiplying. Well, with vectors, this isn't true. There's different forms of multiplications, and each form has a different set of rules, how to do it. This is called the cross product, which is why the little symbol is an X for cross. And it's a different way of multiplying vectors than the dot product. And there's a very formal setup, formal mathematics about how to do it, but as this is an introduction to these concepts, we're not going to worry about the formal math how to do the vectors notation stuff. I'm just going to let you know basically what it means. And what it means is the opposite of the dot product. Instead of trying to find how much of the force is in the direction of motion, or in the distance's direction, we want to know how much is perpendicular. So consider the little picture I drew earlier with the bolt being tightened by this wrench. Notice the size of the wrench. You know, when you go buy wrenches, there are really long ones, there are really short ones. And the reason is because really long wrenches, for the same amount of force, allow you to give more torque. It's easier to turn something with a longer wrench. For instance, why do we use a wrench? Why don't you just use your fingers and tighten a bolt? And if you've ever tried it, you can only go so far. But as soon as you put a wrench, you're just as strong as you were before trying to use your fingers to tighten it. You haven't gained muscle. So you apply the same amount of force, but now with a wrench, all of a sudden you can tighten the heck out of it. And the reason is because the distance from the point of rotation, call it the bolt or whatever, to where the force is applied, that's called the distance, R. Sometimes it's also called the lever arm. It is, what is the thing which is trying to be rotated? The distance from that thing to where you're applying the force is called the distance. At least that's what I'm going to call it. And so the further away you apply this force, the more torque you're going to get, because R is a bigger number now. And then you have F, of course. F being the force you apply. Well, notice if I try to have another situation where here's my wrench, here's the arm of the wrench. If I try to push down on a wrench like this with a force, will that make my wrench rotate? Obviously it won't. All I'm doing is pushing down on a wrench, which is pushing down on a bolt. That's not going to make the bolt want to rotate. The only thing that makes it rotate is if I go this way with it, or this way. That's going to try to rotate the wrench, which is going to rotate the bolt. So notice what's happening. If this line is the distance line, so that's the distance direction, the y direction, then the only amount of force which is going to give rotation is how much is perpendicular to that line. This F, pushing straight down, is parallel. It's a y force on a y distance, but that gives no torque. It doesn't rotate anything. But if I have a y distance and an x force, that does want to rotate it. So this is what the cross product is trying to tell us. You only care about how much of the force is perpendicular to the distance. Okay, that's the big difference here. Given the distance, which is the distance from the point of rotation to where the force is, the torque is given by that distance times the amount of force perpendicular to that distance. And we're going to do some examples to see. So let's take this example. Let's take the wrench. Here's a bolt, here's a wrench, here's the arm. Let's say the wrench is half a meter long. And I apply a force like this. Let's say it's 100 newtons, and the force is applied at an angle of 30 degrees. The question is, calculate the torque on the bolt. Okay, well, what do I know? I know torque is R cross F, that's force times distance. Do I know the distance? Well, the distance is from the point of rotation to the force. That's the length of my wrench in this case, and that's 0.5, so 0.5. What about the force? Well, for the force, I first look at the distance. What's the direction of the distance? In this case, the distance is a y distance because the wrench is vertically upwards. And if you're going to move from the bolt up to where the force is located, you have to move in the y direction. So my distance is a y distance. Because I know that, I now know that the only force must be perpendicular to that. And in that case, of course, it's an x force. So I need to calculate what's the x component of my force. So I look at the problem. Force is pointing downwards at an angle of 30 degrees. If I want the x component of that force, it's 100 cosine 30, which is 86.6. Now that I know the perpendicular component of the force, I just multiply it in. 86.6. Multiply it out, I get 43.3 Newton meters. So you can see this is very similar to when we calculated work. For work, an object's moving in a certain direction, you figure out what direction it is. Say it's the x direction. Now you look at all the forces in your system. You're going to add up all the forces. Of course, if they're in the opposite direction, you subtract, but let's say you add them up. And you only take those forces which are in the same direction as the motion. So I would take all the x component forces. Add them up, multiply by the distance, that gives me my work. Here, we do the opposite. We say, okay, what's the distance? In this case, it's a vertical distance. It's a y distance, the length of the wrench. So because it's a vertical distance, I need the horizontal forces. So I look in my system, all the forces, get all the forces x component only. Once I have them, I add them all up and multiply by the distance. In this case, of course, I only have one force, but that's that. Let's take another example. Let's say we have, here's a good one. Let's say we have a pole which is holding up a sign. Let's say the sign has a mass of 10 kilograms and the pole, we don't know how long the pole is. Call it L. We don't know the number. Let's say for this problem, the mass of the pole is 0. Just to make it easier. For this problem, let's calculate the torque due to the sign. Okay? So what do we know? First of all, I know that the length of this pole, we'll call it L. Next, I know that the sign itself is pulling down with a force mg. I want to calculate the torque. Okay, torque, R cross F. So, first question, what is the point of rotation? Well, if you think about the pole as the thing which is going to try to, if nothing's holding this pole up, I put the sign on the end, then obviously the thing wants to collapse downwards. So it'll rotate clockwise. It'll go this way. So what's the point of rotation? The point of rotation is where the pole is hooked into the wall. Right? That's going to be steady, and the pole rotates about that point. So, because of that, what is the distance from the point of rotation to where the force is applied? Well, what's the force? The force is, of course, the weight of the sign, because it's the sign pulling down, which is trying to make the pole rotate. So what I need for R is the distance from the point of rotation to where the sign is, and that's called L. So L. That's my distance. Now I need the force. but what I need is the amount of force perpendicular to this distance. So I have to ask myself the question, what's the distance direction? Well, if I start at the point of rotation and I try to get to where the force is applied, I'm moving in the x direction, right? I'm moving to the right. So the distance is in the x direction. That means for the force, I need the y direction. So I want the amount of force in the y direction. Well, we look at the sign. What direction is the force? The weight is pulling straight down. Downwards is the y direction. Perfect. Everything's set up. So it's L times the force, which is mg. Since mg is already in the y direction, I don't need a sine or cosine here. It's straight down. mg is everything. So I would multiply this out. I'd get L times the mass, 10 times g, 9.8. And I'd get 98 times whatever the length of my pole is. If it was given in a problem, 2 meter long pole or whatever, I'd just stick a 2 there. Here's another thing to worry about. Torque is a vector. Vectors require directions. So that means torque can be positive or it can be negative. How do I know if the torque is positive or negative? Thankfully, you get to choose. It's completely arbitrary. However, in general, the standard, what most physicists, engineers, and mathematicians say is forces which cause something to rotate counterclockwise is positive, torque. And a force which causes a rotation which is clockwise will be a negative torque. So if we look at this example, the sign pulling down on my pole makes the pole want to rotate clockwise. Thus, my torque is a negative torque. So I'd have to put a negative sign on it. Same thing for the first example. As I apply this force to the wrench wants to go clockwise, so technically speaking, this torque is a negative torque. So that's the basic type of torque question. Given a set of forces acting on your system, they're some distance away from the point of rotation, what's the torque acting on the system? There's another type of question you need to be able to do, and that's balancing the torques. So what's called statics, making sure things don't move. So let's take the perfect example for this, generally speaking, is a seesaw. So let's take a seesaw. It's a plank of wood, let's say. It's balanced out of the center. Let's say this particular seesaw is just a little meter stick. So the length of the meter stick is, of course, 1 meter. And because it's balanced at the center, that means where this little fulcrum is located is the 50 centimeter mark. So this is the 50 mark. And what am I going to do? I'm going to place a little weight, hang a weight from this meter stick over here. Let's let the weight be 3 kilograms. And I place this weight at the, let's say, the 20 centimeter mark. The question is, if I place another weight at the 60 centimeter mark, what weight should be placed there such that this is in rotational equilibrium? This is just a fancy way of saying the meter stick does not rotate. It just balances. Okay? So I've got a meter stick on a fulcrum. It's just sitting there balanced. I then put a 3 kilogram weight at the 20 centimeter mark. And I'm going to have to put another weight. I'm going to say I'm going to put it at the 60 centimeter mark, but I don't know how heavy to make it. The question is, calculate how heavy this weight should be. Now, At first, naively, we would say, well, if it's 3 kilograms on the left, we need to put 3 kilograms on the right, because the left side needs to balance the right side. And the sum of the forces on the left is 3, so the forces on the right should be 3 as well. That would be nice, but it's not true. Because we're talking about a rotation, not just summing the forces and balancing forces, we're talking about preventing rotation. Forces aren't what's important, torques are important. And a torque is a combination of force and distance. So while 3 kilograms may be on the left, where it's placed also is important. So because of that, I don't know what mass I should put here at the 60 centimeter mark. I need to calculate it. How do I do this? This style of question, you do the same thing every time. First of all, you use the fact that if the meter stick is balanced, that is, it's in rotational equilibrium, then if you add up all the torques, the sum of the torques, better be equal to 0. Because if there's some excess torque, then you're going to have a rotation. It's like saying the sum of the forces is equal to 0. If there's some excess force, some net force, then my system must be moving because it's being pushed. Here, if I'm balanced, there cannot be a torque. So if I add up all the torques, it better be equal to 0. All right. Next, I'm going to choose all the torques which go counterclockwise will be positive. And I put it on my little picture just so that anybody who comes around to look at my work can see he made this direction positive. You can make the other direction positive if you want, but you have to be clear. If you don't say either way, then people are going to assume counterclockwise is positive because that's the standard. All right, now all we have to do is add up all the torques. So what are all the torques? Well, I have one torque due to the 3 kilogram mass. So let's say it's torque 1 plus torque 2 is the unknown mass. Those are the only two torques in the system, set it equal to 0. What do we know about torque 1? Well, it's R cross F. So the distance 1 times the force 1. What's the first distance? Well, that distance is from the 20 centimeter mark to where the fulcrum is. Because the fulcrum, the balance point, that's the point of rotation. So I need the distance from the 3 kilogram mass to the fulcrum. Well, that's from 20 to 50, which is 30 centimeters. Okay. Next, I need how much of the force is perpendicular to that. Well, let's see. The distance, first of all, is an x distance, because I'm moving in the x direction to get to the fulcrum. So I need a y force. Well, thankfully, the force is the weight of this mass, and that pulls down. That's already in the y direction. So, perfect. What's the force? It's mg, which is 3 times 9.8. And then we ask, okay, is this going to be a positive torque or is this a negative torque? Well, the way you figure it out is the fulcrum, pretend like you put your finger at the fulcrum. And then you pull down where the 3 kilogram mass is. If you pull down there, does that make the seesaw want to rotate counterclockwise or clockwise? So if I pull down on this side, obviously it makes the seesaw want to go counterclockwise. So this is a positive torque. What about torque 2? Torque 2 is R2 cross F2. Same way. What's his distance? Well, I need the distance from the point of rotation to where this force is applied. So I'm going from 50 to 60, and that's a distance of 10. Next, I need the force, and I need only the amount of force perpendicular. Well, again, the distance is an x distance. I'm moving to the right. So I need a y force. The force in this case is the weight of this mass. And the weight is always in the y direction, so that's good. So I just need the mass times 9.8. Of course, m is the thing I'm looking for here. I don't know what mass to put there, but that's what I want to calculate. Is this a positive torque or a negative torque? We do the same trick. Put your finger at the fulcrum, pull down at the 60. That makes my seesaw want to go clockwise, and clockwise is negative. So torque 2 is a negative torque. Now that I know my torques, I just put them into my equation. I have 3 times 30 times 9.8 minus m times 10 times 9.8 equals 0. I want to solve this for m, so I bring it to the other side. I get 3 times 30 times 9.8 equals 98m. Divide by 98, and we get m equals 9. So what does this mean? This means if I want to balance my meter stick here, then I need to put a 9 kilogram mass at the 60 centimeter mark, not a 3. And of course the reason is the 3 is pulled so far away from the center that it counts more. It feels heavier to the meter stick. Whereas the 9 is really, really close to the point of rotation, so it doesn't count as much. The further you are from the point of rotation, the more the force gives rise to a torque. If you're really, really close, then it really doesn't give much torque at all, because the distance is very small. But if you put the same force really far away, now you're being multiplied by a big distance, so your torque adds up to a bigger thing. So if I wanted to balance this, although it's 3 on the left, I'd have to put 9 on the right if I put it in this particular arrangement for it to balance. Now, of course, if on the right side, instead of putting it at the 60 centimeter part, I put it at the 80, well then the mass on the right is the same distance from the fulcrum as the mass on the left. So if I put 3 on the left, I put 3 on the right. But because I'm putting it closer, I have to put a bigger mass. This is how you go about doing these rotational equilibrium things. You're given a seesaw of some type, a meter stick, a plank of wood, whatever it is. There's some series of forces. Some masses are hanged on it or whatever. And you want to make sure it's balanced. So all the counterclockwise torques must balance all the clockwise torques. How do you do it? You use sum of the torques is equal to 0 as a main equation. And you just look, what are all the torques in my problem? Each one gives rise to R cross F type equation. Some are positive, those that are counterclockwise. Some are negative, those that are clockwise. You plug in everything you know and solve for whatever the unknown is going to be. What kind of unknowns are you going to have? Well, like in this one, what mass do I put there? So you know the distance, but you don't know the mass, so you don't know the force. The other way is to say, the only thing I have in my toolbox is an 8 kilogram mass. I don't have a 9. So if I want to use an 8 instead, where should I put it? Well, in that case, you know the mass is 8, so this m would be an 8, and what you don't know is this r. What should this r be? Well, instead of 10, maybe it's 15, maybe it's 20, who knows what it is? You'd have to calculate it. But those are the things you could calculate. What should I put in this specific location? Or, I have a specific thing, where should I put it? Either way, you're using this calculation to do it. If the object is to not move or not rotate, then you should be able to add up all the torques and they should all cancel out. You set it equal to 0, in other words. So with that, that's the theory of torques. Of course, be on the lookout for another video with a bunch of examples, especially, for instance, With this particular question, the pole with a sign, I could add to it, maybe the pole is tethered with a rope or with a seesaw type. What if my fulcrum is not at the 50 centimeter mark, but it's misplaced? Maybe I balance it at the 40 centimeter mark. How does that affect things? So we'll do some examples with that in the next video. But for now, the important thing to take away, torque, R cross F. R is the distance from the point of rotation to the force. F is, of course, the force, but it's the amount of force perpendicular to the distance. That's the key. So with that, I wish you luck.